Okay, let's quickly see how to calculate the distance from a point, and let us say that point is over here, uh, our point x over here, 3 comma 4, right, this guy. So let's say from this x to this plane which is going over here, to this hyperplane. And yeah, this hyperplane in 2 dimensions anyways, it is a line. But yeah, the generic form of this hyperplane could be, w dot x, w transpose x is equal to, you could have a plus b over here, but since I would, for the sake of simplicity, let it go through the origin, let's just say is equal to 0, right? And this w is given by this vector which is perpendicular to the plane, right? Why is it perpendicular to the plane? By the very definition of this plane, we can prove this to be the case, right? If you take another vector over here which is on the plane and dot that vector into w and say that is equal to 0 because they're orthogonal to each other, yeah, you could eventually come up with this, but that's not much of a problem for now. What we want to show or what we want to derive is the distance from a particular point to a plane, so that when you're doing some algorithms where your plane is the decision boundary, then you can calculate the margin. You can decide on an optimum margin, probably double it and say that double the distance of the point from the plane would be an optimum margin and a classifying margin, be a good decision boundary to say the points on this side of the plane or this side of the margin belong to one class and some other side belong to another class. So yeah, let's jump into it and let us see how do you do this. So let's say this is our vector x bar, you got a w over here. So here we need to calculate this distance, basically this guy from x. If you drop an orthogonal to the plane, you want to see the magnitude of that orthogonal, right? But what we could probably do is, drop an orthogonal from x onto the w, onto the vector that's perpendicular to this, and if I can calculate that projection, that would be a parallel translate of this guy, and it would be equal, it would be the same distance. You could get the distance from x to the plane by calculating the projection of x onto w, right? And visually also it's pretty intuitive that if I draw something from here, dot 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 here, you would see that these two are parallel and they kind of form two sides of a rectangle almost, so they would be the same thing. So yeah, let's do this. Let's try to find out what is this. So if I take this projection to be p, the vector p, right, is equal to magnitude times its unit vector, let us say, we just need to find out this magnitude over here, right? Or you can even find out the actual vector and then get its magnitude, either ways. So let's see how to do this. So we know that the projection would be, the projection of x onto w would be modulus of x cos theta, that is magnitude of x into cos theta. Why? Because cos theta is equal to adjacent, that is p, into by hypotenuse, that is x over here. And from that we could also say cos theta is dot product divided by the magnitudes, right? And then you cancel this out and there you go, you've gotten this one. So what is the dot product of x? And when I say y over here, of course the other participating vector, we chose to call it w for the sake of the plane, but yeah, y is basically w here. So the dot product is what? If you take the algebraic way, 3 into 2 plus 4 into 1, 6 plus 4 is 10, and the magnitude of w is root over 2 square plus 1 square, that is root over 4 plus 1 is root 5, or is equal to 2 root 5. 2 into root 5 into root 5, and that becomes 2 root 5. So there you go. So this is your distance. And then the margin could be, 2 times this, and the margin, an optimum margin could be 4 root 5. And if you want to really just go ahead and calculate this particular point P, that would be is equal to modulus of P into the unit vector, which is equal to 2 root 5, and the unit vector is just giving the direction, and since P is in line or parallel with W, in fact it is almost on W here, you could just find the direction of W. So that would be W by its magnitude. So W is 2, 1 divided by the magnitude, which is again root 5. So this root 5 and this root 5 would go, and you would see that it is 4, 2. And if you actually see P here, if you actually see, I have not really drawn it with respect to the points or something. I just drew it just visually and freehand. But if you see, it's almost there, right? You see, it's actually 4 here, and if you drop it here, yeah, it's kind of going to 2 here. So it is, yeah, slight aberration because of my drawing and writing the numbers with freehand. But yeah, you would see that that also works out. And if you have 4, 2, and then you calculate the magnitude, that would be again root over 4 square, that is 16 plus just the magnitude part I was telling. 16 plus 4, that is equal to root 20, is equal to 4 into 5, so again 2 root 5. So either ways you get this. So this concept is pretty important to get the margin, because in some algorithms like SVM, you may need the margin from the plane, a good optimum margin to decide on a good hyperplane. So yeah, this is the way you calculate the distance and then the margin from a point to a plane. Thank you.